دكتورة أغنيس سيرليوني، في محمد جعفر مرتضى خريجنا، والمهندس حيدر عنبر كمان خريجنا من حبايبنا، وهن مدرسة مساعدة بكلية الهندسة بجامعة يوني في بي ام، مستشارة بقسم الهندسة المعلوماتية، عضو في منظمة الاي تريبل اي نقابة المهندسين الامريكان، ومحكم بالعديد من المجلات الدولية والمؤتمرات، ولها العديد من الابحاث والمقالات المنشورة. Please start.
Okay, good morning everyone. I share my screen. Sorry, I'm not able to share my screen.
Doctor, you should press on present now next to the raise hand.
Yes,
Wait. Yes, but I cannot share it.
Maybe you need permission or something.
Guys, okay, I will try to share mine.
Yes, okay, I see your screen, Jafar. Where do I have to click?
Yeah, probably just give the browser the appropriate permission.
Okay, sorry.
permission. انتوا عاملين permission لواحد ولا الكل مش هنعمل شيء؟ شوفوا other.
Wait a minute, sorry.
It's okay.
No, it's okay. Maybe it's yeah, from our university site. They only give permission for one to present, so we
Okay.
need to. So yeah, we need to make sure of that.
Shall I try?
Why not?
Heather, yeah, you should try.
I can go out and start and come again. Wait.
Yeah, I think I can share.
You can share, Heather? فيك تشارك الشاشة؟
See, yes, I'm sharing, right?
Yes.
Okay, I stopped sharing.
That's why I wanted to connect a couple of minutes before, Doctor.
It's okay.
Okay, maybe Dr. Agnese can send me the.
Okay, here I am again. Sorry.
Yeah, it's okay. Doctor, if you cannot share, maybe send me the presentation and I can present for you.
Okay, thank you. Wait.
Okay.
Sent.
Okay. On my email, Doctor?
Yes.
Okay, got it.
Okay.
Yeah, just a
We
second.
are still trying to give authority to all of you to share.
It's okay. It's okay. Now I can present for. Are you still with us, guys? Yeah.
I think
Okay.
it's okay now. Yeah, we see
Yes.
it. Okay, we see you all and the presentation.
Sorry
It's
for
okay.
this.
Just tell me to move, doctor.
Please.
Sorry. Yes. Thank you.
Go ahead.
Thank you, Jeff. Sorry for this technical issue. Good morning, everyone from Italy. My name is Agnese Sbrollini. I am an adjunct professor here in the Università Politecnica del Marche, and I am the teacher for cognitive computation in physiology and medicine. For me, it's an honor to participate to this conference and to present the topic of my research, what I'm doing every day. Next slide, Jafar. Now, my topic is on the high methods for biomedical engineering. I would like to start with you on the definition of artificial intelligence, because nowadays in our world we talk a lot about artificial intelligence, maybe without knowing exactly what it is. The standard definitions of artificial intelligence are these three that you can see in the slides. First of all, is an area of study in the field of computer science. Thus, it's topic related to how we can decide and develop computers able to engage the human-like thought processes, such as learning, reasoning, or self-correction. It's a very technical topic, because it is strictly connected to math and to optimization science. With time, these definitions start to become more general. Thus, it's also the concept of how we can improve the already designed machines to give them the capability of thinking like a human brain. The idea it's always the same, to have machines that are able to learn, adapt, optimize, and self-correct by itself. And time by time, this definition become really big general, and this is the reason why nowadays artificial intelligence is everything. Because nowadays we would like to have computers that are able to improve our performance, because with time we saw that artificial intelligence sometimes is able to underline process, pattern, idea that we are not able to see. Thus, with time, it starts to be simply a mathematical tool, and it's becoming a sort of philosophy in our world. Next slide. But we try to clarify a little bit the terminology in relation to artificial intelligence, because sometimes when we talk about it, it's really in our idea everything. But artificial intelligence is not the general topic. In fact, the general topic on the biological inspired computation is cognitive computation. This is a branch of engineering, maybe, but also math, also biology, that all the type of algorithms and techniques that we can use and apply that are designed because biologically inspired. For example, one of these examples is the swarm computation, the idea to replicate what usually happens in biology and in nature. Artificial intelligence, our intelligence, is one of the processes in the nature. Thus, it's a part of cognitive computation, and is the science devoted to making machines think like humans. In the artificial intelligence, we have the machine learning, because the intelligence is not learning. We have the intelligence, the organizing, the optimization, the self-correction. But the learning is very fancy, but it's a part of it. And the ability, the tools that give to the machines the ability to learn is the machine learning. Inside the machine learning, we have another big tool that is the deep learning. That's the use of sophisticated and highly complex tool is part of the brain that are able to learn from the data. Next slide. All this technique, the artificial intelligence can be applied in many aspects of our work as a biomedical engineering. Of course, one of these is the machine learning and the deep learning that I already mentioned. But for example, think about the simulation modeling. The digital twins are something that is nowadays very useful to understand the physiology that are behind the specific organs, but also to instruct the clinicians during their practices. Then we have the Internet of Things. That's the idea to connect all the instrumentation that we have in our labs, in our home. In this case, it becomes domotics. And to have everything connected in order to control our behavior, our situation, but also to prevent maybe some dangerous event like falling for aging persons. The predicting analysis, the idea to predict event, to predict severe situation for our health, big data and data mining. Artificial intelligence give us a tool to merge different type of data all together in order to have the common goal that can be diagnosis, monitoring, the evaluation of a therapy, and so on, the visualization, then also the natural language process. But these are some, sorry, the previous one. These are some of the application that we can have in the field of artificial intelligence, but there are also more. Because artificial intelligence is a very flexible tool, thus it means that the limits is only our creativity. Okay, we can use this technique to solve a lot of problems of our work. Next slide. Now, how to connect, because our work is to find methods to help the clinicians, to help medicine and physiology. That's how this technique is merging with medicine. Nowadays, till a few years ago, maybe this is a really recent technology, but till a few years ago, artificial intelligence in healthcare was considered only for diagnostic to support the clinical decision. Nowadays, it's improving, it's enlarged, because nowadays it is used also to improve the patient experience. For example, in the hospital, during the monitoring. In fact, as you can imagine, artificial intelligence enter not only in the life of clinicians that use it to improve the diagnosis or to improve the interpretability of these methods, but enter also in the life of the patient with robotics, with the idea to have robots that can support, for example, in the therapy or in the surgery. But also in the monitoring itself, because nowadays we have wearable sensors, portable sensors that are able also to suggest action to our patient. Next, in this field, all the technique that I already mentioned, like big data, machine learning, deep learning, enter in the medicine through these are 6 examples of how we can use artificial intelligence. For example, for medical products, simply we create new products that involve inside their their algorithm, artificial intelligence algorithm, that maybe are good to estimate parameters, to filter, to the noise, and so on. Or in the diagnostic, thus to support the clinicians in the diagnosis of such pathologies, maybe revealing hidden pattern that we are not able to visualize directly. In the therapy, to optimize the therapy of patients, as I already say, for the preventive care in the wearables, thus as prevention but also as monitoring of our patient. We can use it for personalized medicine, because nowadays we have also artificial intelligence method that aim to create a specialized tool for each specific patient. Thus, a sort of ad hoc custom method. And at the end, maybe the most challenging part, that is opening the box, thus understanding how this machine is thinking and try to interpret the results. That is the part on the clinical interpretability. Next. Now, which is our role? The role of the biomedical engineers is to fill the gap. In fact, nowadays, the computer science part, the technical part is it's working on it. As technicians, we believe in this technique because we saw their efficiency, their very high results. But on the other part, we have the clinical part that is still a little bit confused about it. Also because sometimes we have some information that are not so clear and so interpretable. Thus, as biomedical engineers, we are called to fill this gap and also to properly use this methodology and try to pass this methodology to the clinicians and to the patients in a correct way. Thus, we are called to explain it. Next. So I would like, thus, in this idea that the biomedical engineers are a sort of bridge between the technology and the medicine, I would like to give you some suggestions about the high-based method, the definition, design. And I will give you 4 rules, 4 suggestions that I learned during my experience as a biomedical engineer in the field. First of all, to maintain the clinical aspect of the problem of interest. Because sometimes in the artificial intelligence, in the deep learning, we are used to use technique that can guarantee high performance, but can infer with the clinical aspect of the problem. What I mean when I talk about clinical aspect, for example, we have issues related to the intra-subject variability. The fact that different persons have normal differences that are not related to pathologies or to dysfunction, but they are normality. We are different. This is something that we have to deal with. The second thing is the intra-subject variability. We are different from what we were yesterday. Thus, we have to create also methods that are able to follow the time, the behavior of the subjects, the improvement maybe, or the deterioration of his situation. And at the end, the clinical prevalence. The fact that, fortunately, if we would like to define a pathology, to detect a pathology, usually these patients are less than normal subjects. This is, we are lucky about it, but from a cognitive, from an artificial intelligence point of view, this is not very good, because usually we would like to work with balanced classes and not with unbalanced one. Usually to solve, to have tools with a very high performance, we are used to use trick or tools like the augmentation, the cross-validation, the regularization. There are a lot of techniques that can help us to improve the performance. But pay attention, this technique sometimes can guide till losing clinical aspect of the problem. Of course, I'm not saying that these techniques are not good. They're efficient. Sometimes we are forced to use it because it is the only way to how to understand it. But pay attention, use it carefully, because they can lead you to losing the clinical aspect of your problem. Next slide. The second one is to guarantee generalization. You know that I imagine that you know that generalization is how well a trained model classifying or forecast unseen data. Thus, generalization is the ability to put our model in reality, to use it in the clinical practice. Thus, my idea is that better to have slightly low performance but very high generalization, because it guarantees you to can use your method in the real clinical practice and thus to make the difference. Next slide. Guarantee the clinical interpretability. Thus, apply every time that you create an artificial intelligence tool, you have to guarantee the interpretability of what you are doing. You have to guarantee that it's possible to open the box. Why? Because in our work, we have to give our tool to clinicians. And clinicians, of course, have to take decision on the life of persons, of people. Thus, it means that they have to understand what we are saying them. It's not only a problem of metrics, having high sensitivity, having a high specificity. They have to know which is the reasoning of such problem. First of all, for legal action, because they have to take decision, and it's of the clinicians the responsibility of a decision. First of all, for this. Second one, also to understand the progression of the pathology of the subjects, thus to act on it, to understand which can be the perfect therapy and which can be the perfect suggestion to give to the patients. Next. And at the end, don't forget that we are supporting the clinical decision and the clinical action. We cannot be considered, this tool cannot never will be considered as tool that can substitute the clinicians. Of course, we have to consider our work in support of the medicine and not as substitution. Next. Now I would like to give you a little overview of all the technique and application that we can have in the context of artificial intelligence. Next. The first one is, of course, the feature selection. Thus, we apply here, I reported you the classification of the most important feature selection algorithm. Feature selection consists in choosing the best subset of features among the all available features. We said that this technique works in the field of big data, that we are connecting together a lot of data from several techniques, acquisition techniques. Thus, one step could be to select which are the best of the problem of interest. The first step is, yes, of course, knowing the problem of interest. We cannot eliminate the physiology of the problem from our work. But when the physiology is not helpful, we can use this technique that by themselves can select the feature of interest. One important one is the embedded methods. Sometimes we have a feature selection process inside other artificial intelligence tools. Next, The second one is, of course, classification. Classification is, diagnosis, defining the patients in healthy or diseased, dividing the disease patient in different risk. And here we can start from the statistical method. We will pass through probabilistic one, fuzzy methods. That's the idea to have not defined border, but as a bit of fuzziness. And at the end, the stronger that are the structural ones, such as the decision tree or random forest and the neural networks. Then next we have the clustering. The clustering is the idea to classify without classes. That's the idea to define a group of data according with their similarities without knowing gold standards. These are in our work very, very good because this method allows us also to confirm the clinical guidelines, thus to confirm some evidence that sometimes are confounding, are not so clear. Next one, the regression. That's the idea to predict variables from other variables. This is very strong in case of invasive measurement. Thus, when we would like to estimate something that is not easily measurable, and in this aspect, the regression gives us the possibility to really predict variables such as the cardiac output or the flux in our body that cannot be measured easily and non-invasively on our patient. And at the end, the last one is the next one, the interpretability. That's the idea to open the box, to look inside the method, understand the math that is beyond all this technique, and interpret a little bit what is happening. Of course, this is the recent part of artificial intelligence, the newly developed, and here we have a lot of work that have to be done. At the end, next slide, I would like to show you some opening challenges. There's some little spots that are not solved and about which we have to continue working and updating. First of all, the data quality. We have to deal with the data that sometimes are not good, that are strongly inferred by, jeopardized by noises. And thus we need softwares and applications that are good also in denoising. The clinical interpretability that I said, we have to guarantee the interpretability from clinicians. The dependence of labeling. Nowadays, to apply supervised method, we are forced to use annotation from the clinicians, but it's an hard work for the clinical staff to label. The multimodal analysis, the idea to put images, signals, data, video all together and to interpret it all together, as usually done by clinicians. The computational effort. We have the cloud computing nowadays, thus we solve a little bit this problem, but it's not enough. For example, Haidar will show you with the 3D data that with this computational effort sometimes limitate our creativity. Ethics. We are supposing to take decision on people that how much ethics is all of this. Thus we have to work also with the philosopher in order to have ethical tool. Security, of course, we are working with data that are from patients, that are it does our tool has to be secure. We have to work with cybersecurity, maybe. And at the end, the social substance. As engineers, we like very much this technique, but for normal people, They are very complex, and sometimes the clinicians, are more reliable than our tool. At the end, the next one, my presentation was an introduction of this big work that Haidar and Jafar will present to you. These are two applications of how artificial intelligence can be applied in real clinical scenarios. Jafar will present you the segmentation of anatomical structure of the left heart from echocardiographic images, and Haidar will present you our work on the segmentation of the brain with 3D MRI. Guys, the floor is yours.
Yes, thank you, Doctor. Can you hear me?
Yes, we can.
Yes. Okay, thank you, Dr. Agnese. Thank you, Dr. Hani, for your kind introduction. دوما فخورين بكوننا خريجين جامعة دمشق. So, first of all, I would like to give a summarize about ultrasound. It's a non-invasive, non-ionizing mechanical waves and has much lower cost than any other modality. However, it suffers from low SNR. It's very user-dependent, which makes it very hard to work with the conventional image processing techniques and computer visions. When it comes to heart, echocardiography has many views depending on the location and the orientation of the probe. Some of these views are the apical views, which we see here for chamber and chambers view. Now, these two views are very important because they help quantify the heart representing the heart function in a matter of numbers, such as calculation of left ventricle ejection fraction and the strain rate. Both of these requires accurate segmentation of these images. So the idea of this research was to create an accurate artificial intelligent automated system to perform semantic segmentation on echocardiography images. We wanted to create a system which will take apical 4-chamber and 2-chambers view and reproduce this mask, which has information about left ventricle endocardium, left ventricle epicardium, and left atrium. How we were going to do that? First, we wanted to extract the region of interest, i.e. the left heart, using an algorithm called YOLO, which is an acronym for You Only Look Once. Then, using the output of the YOLO, we wanted to use UNet to produce the final mask. The YOLO, or You Only Look Once, used in this research was the 7th version, which was the lastest version when we were doing this research. And the UNet is a very well-established architecture in the biomedical, especially biomedical image processing. The input is 300 by 20 and 300 by 20 pixel image, and the output has the same size, however, with 4 channel, which each channel representing the probability of this pixel to be a part of this class. This project was implemented and tested on a CAMOS dataset. It's a dataset for 500 patients with only 1,800 available annotated frame. It's clinically realistic because they didn't exclude any patient depending on the image quality, which in practice. Only the insystole and indiastole frames were annotated, and only 3 classes were given, which are the left ventricle endo, the left ventricle epicardium, and the left atrium.
Sorry to interrupt. We only have 5 minutes, please.
Okay, Prof. So we split the data frame into training, validation, and testing. This is the output of the YOLO algorithm. And this is the output of the UNet, which we can see this is the ground truth, and this is the predicted mask, which are very similar. Numerically, we reached 92% for dissimilarity coefficient for endocardium and 85-87 for epicardium left atrium. Finally, this system by using YOLO and UNet because it didn't separate it between 4 and 2 chamber images. It was able to work with low resolution images, segmenting 3 regions with something we don't find, like we rarely find in literatures. And we only were restricted by the available annotated class, but we think this idea can work for even more classes as long as we have more. And if you are interested, you can read more about it in a paper we published in Diagnostic journal under the same name. So now Haidar will present his. Haidar.
Yeah. Can you see my screen?
Yes, we can.
Yes.
Just please as quickly as possible.
Yeah, for sure, bro. Thank you for this introduction. My project about cerebral structure segmentation from 7 test and magnetic resonance scans using deep learning. Cerebral structure segmentation is an essential process in several clinical and non-clinical analyses. It's good for measuring and visualizing the brain's anatomical structures, for analyzing brain changes, and for diagnosing, monitoring the progression of the neurological disease. This work aimed to introduce a fully automatic brain structure segmentation method based on an encoder-decoder deep learning model from 7 test MRI scans to segment the whole volume of the brain into 6 structures: gray matter, white matter, basal ganglia, ventricle, cerebellum, and brainstem. This is a 3D presentation for these structures. It shows the complexity of these structures and how they are located within the brain. And this work adopts the well-known deep learning model unit, which contains the downsampling and upsampling path, encoding and decoding path. The investigation process for this work was divided into 2 scenarios. The first scenario was to inject the whole volume of the brain in the model to extract the 6 structures. The second scenario divided into 2 steps. The first step was first to extract the brain by removing the background of the skull. And the second step was to segment the extracted brain into 6 structures. And finally, I checked the behavior of the segmenting model in the case of the ideal brain extraction. The most common evaluation metrics used for semantic segmentation are the dissimilarity coefficient, volume similarity, and hazard distance 95%. This is a test sample. You can see to the left the predicted mask, and to the right is a grounded truth. This is after applying the predicted mask onto the MRI scan, also for the ground truth. And this is the 3D rendering for these extracted structures. To the left, you can see the whole brain. To the right, you can see the white matter and the other structures. Numerically, for the dissimilarity coefficient, the higher is the better. For 2 sample tests, you can see for the 6 structure, for most of them, we obtained more than, for most of them, 90%, more than 90%. For the volume similarity, also the higher is the better. We got for the 6 structure as well for the same test samples, over 96%. For the hazard distance, the less is the better. For most of the classes, we obtained less than 3 millimeters. The 3D data processing is a challenging task since it requires a high hardware capabilities. And this work I moved to the cloud computing using Google Colab Pro. I decided to perform the training onto the whole volume of the brain to take advantage of the local and the global information. The training was done on the architecture was built from scratch without adopting any pre-trained model and without performing any pre-processing or augmentation. Due to the technological constraints, I had to keep the deep learning architecture with a low level of complexity. It wasn't possible to increase the batch size for over or more than 1. And it wasn't possible also to do the fine-tuning procedure that allow us to generalize our model and to perform the segmentation from MRI from other sites. But finally, we can see that we succeed to obtain an optimized 3D unit model for automatically segmenting the whole volume of the brain into 6 structures at 1 in few seconds. And with a great group of researchers from University, we managed to publish a paper at the MTPI with the title of Double-Stage 3D Unit for On-Cloud Brain Structure and Multi-Structure Segmentation from 7 test MRI scans. It was our second scenario of our work. Thank you for your attention.
Thank you very much, and hope to see you here in Syria next conference.
Thank you.
Bye-bye.
Thank you.
Hopefully, Professor. Thank you so much.
Thank you. We also hope.
Thank you.
Thank you, Doctor.
I was running.
الاتصال اللي بعده